All right, so in this example, guys, we have a graph. And what I want to do is talk to you about identifying the domain, the range, the discontinuities, the boundness, end behavior, increasing, decreasing, constant intervals, x and y intercept, as well as even or odd. And I think that's everything I had up there, right? Oh, I didn't cross Extrema. All right. Everything we're going to talk about, what we want to know. All right, so in this first example, let's talk about the domain. So when we're looking at the domain of a graph, basically what we are concerned about is the values of x that are defined for the function. And a really kind of easy way to kind of look at that or think about that is just basically saying, like, how far to the left does the graph go? How far to the right does the graph go? Right? I mean, that's really, we're just looking for the set of all x values to make it the function. So a lot of people will look at this and say, well, it looks like we're good. Because even though there's an undefined value here, there's a point above it, so it's covered, right? So we're covered in that respect. And then it just continues. It continues going to the left and continues going to the right. So I saw a couple different pieces of notation from previous classes. They said all real numbers like this. Some even wrote out all real numbers. They wrote like that. Some people even wrote this. They used inequality notation. All right, which is perfectly fine. Those are all OK. And on a free response, depending on what my directions are, those would all be acceptable. In this class, though, we're primarily going to be working with interval notation. And interval notation is basically saying how far left to how far right. So you're basically just creating an interval of one value to the next. And since infinity is not actually a number, you can't have infinity of anything. It's not contained. So that's why we use a parenthesis rather than a bracket. All right. On contrary, the range, if the domain is the set of all x values, the range is the set of all y values. Right? Here's x, right? And here's your y. So the range is the set of all y values, basically asking us how low does the graph go to how high does it go. So the lowest the graph goes is it looks like it's continuing all the way down to negative infinity. But the graph continues as high up as 1, 2, 3, right? Yes? No? And 3 is contained. It's a part of the graph. It's a value on the graph. So therefore, that's why we're going to use the bracket. All right? The next one is discontinuities, or we want to determine, is the graph continuous? And basically, guys, if the graph is continuous, that means we can draw or trace the graph without lifting up our pen or pencil. So as you guys try to do that, you notice that we kind of come to a hole, that we have to skip over that hole to continue graphing. Correct? And then we have to actually fill in that point and then come back and do that. Yes? So it's non-continuous. It's only continuous if you can just nice graph it without lifting up your pen and pencil. Now, so we would say it is continuous. I'm sorry. We would say it's discontinuous. But a lot of times, the question is not going to say, oh, is it continuous or discontinuous? Like, that's kind of obvious. More of the time, we want to ask, what type of discontinuity is there? If there is a discontinuity, what is there? What type of discontinuity is there? So this, if you guys look in this graph, you can see this graph is perfectly OK, except there's like a missing spot here, right? And it's really just one value that is undefined, which we call a hole. Now, a hole is what we call a removable discontinuity. So I'm just going to put this over. When you're looking at discontinuities, you have removable and non-removable. And like I said, guys, this is like in your notes, but it's just, I think a good thing for you guys to remember. Removable is like a hole. Non-removable is like a jump or a vertical asymptote. So if you have a discontinuity that's a vertical asymptote, it's non-removable. And if it's a jump, it means you're going from like one function to the next, that would be a non-removable as well. So we would say this is a removable discontinuity at x equals 0. All right. Now, again, it all kind of depends on the frame of the question. Up here in the problem, I just say, hey, continuous or discontinuity. So sometimes I might say, hey, label the discontinuities. Or where are there any discontinuities? Or it might just say, hey, is the graph continuous or not? Right? So I mean, there's a lot of different questions I can ask from you. The main thing I want you guys to understand is this is a removable discontinuity. So you could say it's a hole, which is removable. And there's a location of this discontinuity, which is the x value at 0. All right? I'm actually going to skip ahead to Extrema because Extrema makes boundness make sense. So when we're looking at Extrema, basically what we're doing is we're looking at the maxes and the mins of the function. So we basically want to know, is there points that are highs and lows of the graph? And you can look in here, and we could say, oh, there looks like there's a couple different highs and lows here. Looks like if you look at this, the graph only goes as high as these 2 points. Correct? And the other definition, or the best definition for absolute maximum, or for maximums and minimums, if you have a maximum point, and this makes sense to you, or it should. If you have a maximum point, that means every point to the left and every point to the right should be below that point. Would that make sense? Yes. And a minimum point would be any point to the left and any point to the right should be above that point. Correct? So if we kind of look at this graph, we kind of say, what is this? This is supposed to be at -2. If we look at these 2 points, we kind of notice, hey, if I pick a point to the left and I pick a point to the right, they're below this point. And that's true for this point as well, right? Now, not only are these the highest and the lowest points, these are the highest and lowest points of the function, correct? There is not one point that's even higher than this. Would you guys agree? So this extrema, these are what we call absolute extrema. Or we could just call them absolute max. So they're absolute maximum values. Now, there's a couple different ways we can talk about absolute maximums. We could talk about absolute maximums of where they occur. Where do the absolute maximum occur? They occur at -2, at x equals -2, and at x equals +2. We could also talk about the maximum values. What are the maximum values? Well, the maximum value of this graph, the graph does not go any higher than y equals 3, right? So we can talk about, when we're talking about extrema, we can talk about where and what. Where is that maximum or minimum? And what is the maximum or minimum? Do you guys agree with that? So just be careful when you guys get to like testing portions. Make sure you're answering the correct question. It might be where or it might be a what. All right? A lot of times you can get around that by just saying there's absolute maximums at -2, 3, and 2, 3. So by giving the coordinate points, you are now providing a location and a value, right? You're saying the location occurs at the x value, and the absolute maximum value is 3. And you can have more than one absolute maximum, as long as it follows in that definition. Now, this one gets confusing, or this one looks good, because once you guys agree that this looks like a point to the left and to the right, this should be a minimum, right? But the problem is that's not actually a point. So you can't say 0, 0, because 0, 0 is undefined. Let's look at the point 0, 1. If you look to the left of 0, 1 and to the right of 0, 1, is that below 0, 1? Look, you're not looking. If you go to the left or to the right, is that below 0, 1? Yeah. So guess what? That's a maximum. Now, the difference here is, all right, so you guys have my camera, right? If you take my camera and so we're zoomed out on this graph. Now, if we take my camera and we zoom in on this graph, and we can only see that portion, does that look like a maximum? Well, actually, let's get even closer. That's not a good zoom in. Let's get even closer. What about if we zoomed in, so all we saw was this? I'm really zooming in really far, right? Is this point now more clearly a maximum? Is this now point you can definitely see that that's a maximum point on the graph, right? But as we zoom out, we notice that there are values that are higher. So when we're talking about maximums or minimums that are the highest of highs or the lowest of lows, that's where we use the word absolute. When we're just talking about a maximum that's within a given range or interval, we call that relative. Or you could say local. And that's a relative max. So the relative max occurs at 0, 1.
So is the relative max like the lowest mass there is?
Sorry?
Is the relative mass the lowest one there is?
The lowest. So if there's a minimum, then, but in this case, we don't have any minimum values. There are no minimum values. There's no point that represents a minimum, right? Because you would say if this was filled in, then you could say 0, 0 was a relative minimum. But it's not filled in. It's open. And then obviously it continues down, so it's never an absolute. OK? Now, boundness comes in, guys. If you get stuck with boundness, the best way I like to think about boundness is just replace boundness with restriction. OK? Basically, this is saying where are the restrictions on the graph. When we looked at end behavior, I think only one group talked about end behavior on their things. When you talk about end behavior, you're basically saying the graph is continuing like without bound, or it's boundless. Think about the word bound and boundless. If something is continuing boundless, there's no restrictions on it, correct? Like look at this graph. Pretend it's like a roller coaster or something. As you continue on this roller coaster, you're going down to infinity, right? There's no restrictions on how low you're going to go down. That make sense? So you are unbounded down here. You are unbounded below. But are you restricted on how high you can go? Yes. Yes. So you are bounded above or restricted above. So we just say bounded above. And to give you guys a quick and easy definition here, or a quick and easy way to remember it, that's bounded above. That is an example of a function that's bounded below, because it only goes at a certain value. If you guys want an example of unbounded, that function is unbounded, because there's no restrictions, right? It's unrestricted. It continues indefinitely in both directions, right? If you want something that's bounded, top and bottom, like that's an example of something that's bounded above and bounded below, because it's restricted on how high and how low it can go. Does that kind of make sense, right? So you just look at your restriction. It's bounded. It can't go only high, so it's called bounded above. Yes?
Wait, so boundness only applies to the endpoints? It doesn't like for like 0, 0 where it's like a whole, that doesn't?
Yeah, we're just looking at kind of like the function in general. Is there a restriction on how high it goes or how low it goes? And if there is a restriction on how high, then we'd say it's bounded above. Or we could say it's bounded above. OK? The next one is end behavior. And so end behavior, we're going to spend a lot more time on this once we get into polynomials. So all I really care for you guys, there's a lot of different notations that we're going to talk about. For right now, non-mathematical is perfectly fine. All we're asking for end behavior is as the graph continues to the right and to the left, where is it going? Up or down? Or, be careful, it doesn't always have to be going up or down. It could actually approach a number, or it could stop, and therefore there would be no end behavior. Okay? But in this case, we have a pretty nice function here. This graph, as we continue to the left, the graph is going down. Usually we'll say falling, or at least I prefer to say falling. As we go to the right, the graph is falling. So we could just say, I prefer falls left and falls right. That's a little bit more descriptive than down, down, up, up, positive, positive, negative, negative. And don't worry. Yeah, I mean, don't worry. Really, I don't really care too much about this, because next unit, we're going to have a formal definition for end behavior. So the falling positive is not really going to, we're going to have a mathematical definition. All right, increasing, decreasing, and constant. So actually, let's do x and y intercept real quick, and even or odd. And then I'll do increasing, decreasing, constant. So in the x and y intercept, you can see that here it looks like it, but since it's an open hole, there's no x-intercept. So you can see that it's crossing at -1, 2, 3, 4, and 1, 1, 2, 3, 4. So the x-intercepts, you could say at x equals -4 or x equals 4. You could also write them, ladies and gentlemen, as coordinate points, which is my preferred method. And the reason why I like writing them as preferred method, because it reminds my brain that when x is equal to -4, y is equal to 0. And that is very, very important later in this whole unit of understanding the intercepts. Y is equal to 0 for the x-intercepts. And if I wanted to find the y-intercept, we just look at where the graph is crossing. And you could say the y-intercept is at y equals 1 or 0, 1. So the y-intercept is when x is equal to 0, right? It's trained into my brain. Guess what? If something is symmetrical about the y-axis, it's even. Everything to the left of the y-axis is equal to everything to the right. So it's even. If something is symmetrical about the origin, got to kind of follow me on this one. If you flip it about the y and then flip it about the x, you get the exact same function back. So that's called odd. And if you guys look at this graph, you guys will see that this graph has symmetry about the y-axis. So therefore, it is even.
I know it's even or odd again.
If it's symmetrical about the y-axis. Everything to the left of the y-axis is equal to everything to the right. If it's symmetrical about the origin, that means you can flip it around the x and the y-axis, and it gives you the same function. All right, increasing, decreasing continuous value. So this one gets pretty confusing, and I think reading the last group's description kind of like helped out with that. So when we're doing increasing, decreasing values, everybody usually has a different take on this. And I want you guys to kind of understand something. Like if I'm describing this graph, there's a couple ways we could talk about this. We could say, how is the graph increasing, decreasing, or continuous? So let's actually look at the interval from 0 to 1, 2. So from 0 to 2, right? I could say the graph is increasing from x equals 0 to x equals 2. Yes? Does that make sense? So if I'm talking about location, I would want to use the x values, right? I'm saying from x equals 0 to x equals 2, the graph is going up. Does that make sense? If I say the graph is increasing from y equals 0 to y equals 3, that's basically giving me the values of how high it's increasing and how high it's increasing from one interval to the next. Does that make sense? All right? So if you're talking about x values, you're kind of talking about location. And y values, you're kind of talking about the value of how high or low it's going, right? So when we are describing something as increasing, decreasing, or constants, we only want to talk about when is the graph going up, down, or when is the graph going up, down, or remaining constant. So what that means is even though these have coordinate points, we don't care about the y values here. I don't 1, 2, 3, 4. I am not going to use the y values. So when I talk about when is the graph increasing, I say, well, it looks like the graph starts from -infinity to -2. I don't need 4 of these. From there, from negative infinity to -2, the graph is increasing. Would you guys agree? So I'm going to say my increasing value is from -infinity to -2. Then does the graph continue? Does the graph increase on any other interval? Is it going up or down on another interval? Yeah, from 0 to 2. Now, what I want you guys to understand, these are not coordinate points. If you guys look at my definition on the board, it says when is the graph going up, down, or constant. So when you're writing your increasing, decreasing intervals, you're explaining this, you're describing this with x intervals. When is it going up, down, or constant? And then it is decreasing on the interval -2 to 0. And then on the interval 2 to infinity. All right, so I spent a whole bunch of time. I didn't really take too much time breaks. Does anybody have any questions or anything that I kind of covered? Yes?
So for the maximum and minimum points, do they always have to be in the graph, or they can be like that black point?
No, yeah. So like if I had a point like up here, like that's my new max. right? I'm never going to have a minimum, though, at least in this graph, absolute minimum, because the graph continues indefinitely without bounds going down, right? But as I mentioned, like if this was filled in and like that wasn't there, then that would be a relative minimum, because points to the left and to the right are above that.
Yeah, so like the 2 points at the top, how you said they were both like a max and min?
No, they're just both maxes. They're not both mins. These 2 points are both maxes. They're absolute max. -2, 3, and 2, 3. Good? Anybody else? Anything?
Sure.
Yeah, you can take a picture. I'm going to leave this on the board too, and if you guys need, because we're going to do an activity. All right, so